Now. Okay, so everyone, welcome. I have just started the recording, so everyone should be aware of that this presentation will be recorded, but it will not show on the recording who is participating or not, so only if you ask questions afterwards, you will be in the recording. The recording will be put online this afternoon, also with the last presentation that we did last week. I have just organized that, so it will be online this afternoon. So then, okay, Gaylord, I give the word to you.
Thank you very much, Esti, for giving me the opportunity to present my work. I am Gaylord, and I am PhD candidate now at NTNU, the Department of Civil and Transportation Engineering. At that time, now it's the Department of Civil and Environmental Engineering, IBM in Norwegian and Cycle. And I'm going to present to you a little bit about our research topic and share with you a couple of results that we have achieved and what we are about to do for our future steps. The research topic is entitled Life Cycle Assessment and Sustainability Thinking in Large Infrastructure Projects, in big infrastructure projects. And as a short plan of what you are going to go through this morning, I will present you a team because we work in team. Then I'll talk a little bit about my project and the motivation for doing the project. Why are we doing it? Why are we focusing on things that we are looking at? The research approach that we are using, the pathway to get to the results or to achieve our goal. I will elaborate a little bit more about it also. We present you some selected results. And,
Gaylord?
Yes?
Could I just ask you to start your video so that we could see you also? Because you will be in the movie afterwards.
Okay.
So just seeing a blue picture with your name is...
So
it will be more interesting to have your face.
Then I should look for the video. Where is that video?
It's on the bottom.
Okay.
You have a blue mark.
Mm-hmm. All right. Display.
And all of the others, we mute our systems, and you can continue, Gaylord.
Yes. I'm trying to find my video. Okay, yes. Then like this. Can you see me though? Can you see my video?
Yes, now I can see you. Now I can see you. Okay, continue. I will mute.
Okay. You can still see me? Okay. So, a little bit about let's go to him. And we focus on environmental impact assessments and cost analysis of roads. And our emphasis is put on tunneling and tunnel maintenance, open roads, traffic, geometric design, maintenance activities, and a couple more, but those are the main points that we are looking at, and we consider the roads throughout its entire life cycles. So the main goal is to facilitate decision-making process for different road options. So how can we site the road, put the alignments, where should the alignments go, how should the alignment be designed. We are not road designer, but we are trying to advise the team that if you design the alignment this way, you site it in that way, you will have fewer or less or much better environmental profile. Then we want to improve the environmental profile of the infrastructures, the linear infrastructures. It can be a road, it can be a railroad, but our focus actually is on roads. And we want to enable accessibility and mobility where it is possible. So my project has a title, and the title is The Effect of the Geometric Design, Surface Characteristic and Vehicle Technology on Environmental Impacts of Big Infrastructure Projects. And some basic information about my project. I work on big infrastructure projects here, and mainly linear ones. So we look at roads and railroads, and my focus on roads, Norwegian context. My main project or my main case study is the E39, both the old and the new alignment that is under construction now. Whenever we have information, I try to use it and I try to assess it. And I look at some key factors, which are the geometry, the surface properties, the vehicle energy demand, and the traffic in its entire mixed. And the main goal is to quantify overall environmental impacts and assess the impacts and try to improve those impacts. I try to understand how the geometric design influences the overall environmental impact profile of linear infrastructures. And once I get a correct understanding of it, so I will try to improve the geometric design in order for us to reduce those impacts and get a better profile. So my main tasks are quantification of environmental impacts from earthwork, surface works, operation, use, and maintenance of the infrastructure. And then I develop a methodology to isolate the contribution of the geometrical elements in the overall impact profile of the infrastructure. And I understand the role played by the traffic, the vehicle technology in combination to the geometrical elements that I'm assessing into the overall impact profile. And once I have the impact, I try to assess them. Why are we focusing on the geometry now? Because we have a team working in different parts of the road, and I'm focusing on the geometry. Here is a couple of reasons we are doing it. If you do a quick research, we could understand that 45% of vehicles' useful energy demand is due to the geometry. And if you look at the whole picture, we have the infrastructure in one side, and then we have the traffic in the other side. So the infrastructure will include the geometry, which is what we are looking at. And then you have in the geometry, you also, in the infrastructure, you also have the surface. Then you have vehicles using those infrastructure, and those vehicles have different technologies, and they use different type of fuels. So when they are interacting with the infrastructure, the geometry is playing a role, which is a key role, because when you put your fuel in the car or in the truck, then you try to use the truck on the road, then the useful energy that you are using, the useful energy that you need for you in order for you to create work, 45% of those energy is just induced by the geometry. So the geometry is responsible of 45% of the energy, the useful energy of the truck. So it is worthwhile looking at it. And if we look at it, we can get better achievements. But how are we going to do it now? What are we considered is the infrastructure in one side and the traffic in the other side. And what we are quantifying are materials, water, energy, emissions, waste, and land use. And how are we quantifying those? We are using the life cycle thinking approach, as the topic is stating it, and we use life cycle assessments, and we use life cycle impact assessments. And if we have time, we can do some exegetic combined to environmental analysis to try to get a clear picture of what we are doing. And the main goal is to find which combination of geometry and surface will lead to the best environmental impact profile I have to underline here that we are assessing, I'm working on the environmental dimension of sustainability. So I'm looking more in the environmental profile, and there are other team members who are looking in the cost, and some other people can look also in the social aspect of the environmental profile. The word best here is defined by us. So it's when we say best, we have to tell you what we mean by best. And here, best can be, for example, with respect to one indicator. Maybe we say the alignment that will achieve less CO2 emissions. And if the least CO2 emitting alignment is found, and for us it can be best. So best here is totally flexible, and we should not think that it's the best of best. When we use life cycle assessment or life cycle thinking approach, there is one thing that you have to do. Any researcher has to do to present his system and show the boundaries of his system. So for this research here, we present you the system boundaries. What are we going to which are the boundaries within which we are trying to act, we are trying to conduct our research. So if we look at the whole road project, we have many stages in the road project. We have the planning, the design, the construction, operation, maintenance, and use, and then we put them in one box. We call them use, and then we have the end of life of the infrastructure. So our analysis is not going to look at all the stages of the road. Our main focus will be on two stages, which is the use and the construction. And in the use phase, we also include the maintenance and the operation of vehicles. And we don't have enough time to try to look at the construction, which is end of life, what will happen to the infrastructure at end of life. But we don't say that it's not important. It is important indeed, but our main focus is on the two boxes that we have. So the construction phase and what we call here the exploitation or the use phase here. And in the construction phase, we try to look at material extractions, which material you are using to build the infrastructure, to build the surface, and you are doing some earthworks, and you have construction effects. So all those things will have some release to the natural environment, and it will have some impact to the nature also. So we look at those. We look at the exploitation phase when you have vehicles. The road is done and then is ready. You need vehicles to come and exploit them. You will need to maintain the roads from time to time. The vehicles are using the road, and they are emitting themselves because they are using fuels, and those fuels can be polluting. And then we look at those also. We also look at the statical element that we have in the infrastructure. From time to time, you need to have some lighting system to the infrastructure. You try to build new fences, or you try to do different type of interventions. So we look at those interventions as well to see how they can impact the whole structure. And we proposed a research approach in order to do that. So here you have a diagram of the approach that we are trying to follow. Very simple, and I guess it can be very clear to you. So we have infrastructure in one side, which is static. Once it is built, it is there. So you don't really have to come and change the complex infrastructure when it is built. So you will try to do some small intervention. But you have traffic in the other side, which is dynamic. So traffic doesn't really depend on us. So today we may have fewer, tomorrow we may have higher volume of traffic. So we try to combine the two of them, infrastructure and static. And what we do is we look at the geometrical elements, so the geometrical factors, and we say, okay, when we design the road, we have those geometrical elements that we can look about. Here, for example, we look at the grades, we look at the lanes, we look at the curve length, and segment length as well. And when you design this, you design the infrastructure, and those geometry are inducing a certain behavior of the equipment, of the vehicles that are using the road. So we get both, we try to capture both emissions during construction, when the infrastructure is constructed, is built, and then when it is used by the vehicle. So we combine all those things, and we try to do some differences. We do some calculation, and then we will be able to present which can be the best options. So which geometry, if you try to follow it, will lead us under a given traffic conditions, it will lead us to fewer emissions or better environmental profile. And once we have those elements done, calculated, we use life cycle assessment and exergy analysis, and then we use life cycle impact assessment to assess the impact that we'll have. So for the infrastructure, what we consume, what we need is what we call here life cycle inventory inputs, which is everything that you need when you are building the infrastructure. So everything that you are using, machinery, materials, everything that you're doing, any type of intervention is a process, and we have those. We know how those processes are evolving, which type of impact they are doing in the environment, or which type of release they are actually wasting to the environment, and then we get those input values, we put them into our models, and then we look at the use phase, what the vehicle are actually, how the vehicle are performing, and which type of emissions they are just releasing. We combine everything, and we look at everything in combination to the geometry and the surface of the road. Then we try to run our model to assess the environmental impact and to pick one profile that can be desirable to us. And here is the responsibility of the decision maker to say, okay, for me, what I think is desirable or achievable or, I don't know, feasible, I'll get back to that at the end, is this alternative. Then he selects, he goes. So he will have kind of control of what will happen in the future with the infrastructure. Here is the status and the timeline. So I didn't start this year. I started in 2015, and I've done a couple of things. So I look at if I stick with my own system boundary. So I've been looking at quite a lot of things. So I've been looking in things that you see in green, in full green, I can say, and the light green. So the full green means I have full control of those things. I have done some work, so I understand it much better, and I can provide good advice and recommendation when it comes to those things. So when it comes to use and operations, we have a good understanding of that for the whole team. And the light green is what we are trying to integrate in the whole model, and we do have a certain understanding of that. For some reasons, we don't want to claim anything for the moment, but it doesn't mean that we don't understand how it's working. We do have a good understanding, and we still have to improve it more and more in order for us to be in position, to get to the position to tell, okay, we can advise you about this now. And then we have like 70% of my time, so I think it's a good progress. Now I will elaborate a little bit about the approach that we are using. And before that, I have to talk a little bit about the emission in road transport. So road transport has two main sources of emissions. You have the infrastructure. When you build the infrastructure, construction first, maintenance, reparation, extension, any type of intervention you are doing, you will use materials, you will use equipment, you need energy inputs, you will use some water. So all those things may have or not an impact to the natural environment. So this is one source of emissions or of environmental impact in road transport. And the other source is the vehicle, which I used to call road users, so because vehicles are the true road users. And we may not have a road, we can use our foot to go, but if we don't really have a practical infrastructure, it is difficult to use the vehicle. So vehicle needs the infrastructure to be there, and then they are the real road users. And when you use the vehicles, depending on the powertrain or the system, their technology, they will emit or not something during their operation. So this is also one of the main source of emissions in road transport. And when we talk about emissions in road transport, there are a certain category of pollutants that we want to look more on it, that are maybe of concerns. So some pollutants, and we group them in different categories, also subcategories. We have pollutants that are ozone precursors. So once they are released to the atmosphere, they are more likely to involve in ozone. So they can contribute a lot in creating ozone in the atmosphere, which is really not good for people, respiration system and things like that. So imagine yourself that you are driving in a tunnel, and then the level of ozone, which must be at a certain level of a certain number of ppb, amount of parts per billions, is just getting higher. And then if something occurs, or maybe you are stuck in that tunnel, and you don't have a proper filter, I don't know if you can filter that, you will try to absorb it in a way or another. So ozone can be very detrimental to human life. And then you have pollutants that are more likely to evolve in greenhouse gas manner. So you have CO2, you have CH4, you have also N2O. And then we look at some acidifying substances. We look at some particulate matter which can pollute the vision and also pollute a lot in the respiratory system. Some other components are carcinogenic. So once they attain a certain level, they will create problems that are very difficult to inverse, and some toxic substances, and you have heavy metals that are normally used to go to water ecosystem, to the soil, and then they get back to the food chains, and we eat them, we consume them, then they create different stuff that we don't like. And the road vehicle emissions flow diagram can be simplified in the way that you are seeing in this picture, which means that the vehicle will emit anyway, according to its powertrain. The vehicle will emit anyway, even if it is not moving. It is not in motion, but it will still emit. And most of the time, the emission that you have when the vehicle is static is related to evaporation of fuel. So fuel will evaporate depending on weather conditions. It will try to go up because of the vapor pressure of the fuel compared to the vapor pressure of the air. And then substance will go out, which is also amount of pollution that should be quantified. And then you have several other steps of pollution occurring all around the vehicle. So you have pollutions from vehicle tire and brake wear. You have pollution for the road wear, and you can see on the picture. You have pollution for evaporation as well, because the vehicle is in motion, but still, if the vapor pressure of the fuel and the air allows it, it will keep evaporating. And then you have exhaust emission from combustion. Please? From combustion of the engine. And in many cases, it is not easy to quantify evaporative emissions. It is not easy also to look at vehicle tires and road tires. What people used to do is to look at combustion, which is somehow well known and easily handleable. So we are trying to look at exhaust combustion emissions. We are also trying to include evaporative emissions and some tires emissions according to models that are available to us. So we proposed a concept. We proposed two concepts in order to get there, because we have to evaluate the geometry of the road, and then we have to evaluate, to assess the geometry of the road and look at a better profile environmental-wise. So we are not road designer, and when they design road, maybe we are not there. So we have we must be able to tell to people, okay, this geometry is performing well, this one is not performing well, not really being a road designer. So it is a little bit difficult for us to try to do that. So we developed a concept that we can follow with the methodology what we are using and the concept that we have, which will enable us to try to combine the geometry with what we are trying to look at. So two concepts are put in place now. One concept is called single level approach. which you can see in the flow diagram here. And if I can explain it quickly, very quickly to you, is that we look at the infrastructure. Here we are at a stage that the alignment has been designed by a contractor or a company, a consultant that designs the alignments for the national government or the local authority. So they came out with designs, and they didn't come out only with one or unique design. They have several alternatives. So they bring it to you guys at Statens vegvesen or somewhere else, and then they say, we have those alignments. We think you can decide among them. They give you cost information that you can decide for. So as environmental evaluator, or we try to assess the environment. You get it and you say, I want to see how this alignment is performing environmental-wise. So you have one approach that you can use and check, see if it will give you something that you really desire, or if you want to have more control of your alignments, you can advise them and say, look, I think this alignment is more polluting, maybe CO2-wise or NOx-wise, and we would like in that area, given the weather conditions and given that the fact that it's a much dense area, we would like to see a less emission with regard to NOx. So we use two concepts. The first one is a single level approach, which is relatively simple, which is about using those, the information that you got from the designer, the alignments actually, and I have to say that we are looking at the vertical alignments, and then you have the surface information, and you say, okay, this is it, and then you pick one vehicle category, and you say, I will assess this alignment based on this type of vehicle, and you should argue about the category that you selected, and I'll help you with that. So we have a table helping decision making about those process. Then you select the type of vehicle, you try to match it with the vehicles type that we have in our database, because we provide you a tool with a database. And then once you find the corresponding vehicle of in the database, then you can run our model, collect some information about factors that can be fuel consumptions, that can be emissions with respect to CO2, to NOx, or to particulate matters. And then you do the environmental modeling. You are not supposed to do it. The tool will do it for you. And then you run the optimization, and then you get some results. So the first result that you will get is that you take the alignment as it was given to you, you assess it, which means you take the alternative, you pick a type of vehicles, and then you say, okay, I want to assess the alignment based on fuel consumption. Then you get the fuel consumption of the existing alignments those existing alignments that have been given to you. Maybe let's say, for example, you have 10 kg for the whole alignment for that vehicle. For one alternative, for the other one, you have 12. For the other one, you have different numbers of them. Then you should be able to decide. If you think that you can just go and pick the fuel consumption and pick one alignment, it's your decision. But we help you to go some step further, which is now you can make a decision. You say, what will happen if I want the alignments to give me, if I want to reduce the fuel consumption, for example, by 5%, which type of alignments am I going to end up with? So you can make those type of decisions, a kind of what-if analysis. If I want to decrease the pollution by 20%, by 20%, by 5%, and so on. So we have a tool that can help you doing that. The reason why we do that is because then we have several alternatives. We have several geometries that we can evaluate first during use phase, which is easy, and then second, to conduct a life cycle assessment of those alternatives. So we can have billions of them according to the model that we are running, but we cannot do billions LCA at the moment. So we need to end up with some few alternatives and then evaluate them, assess them in a very logical way that can help us have a clear a clear view and make a better decision. So this is the single level approach. When you have one vehicle, you base yourself on one vehicle, one typical technology of that vehicle, and then one typical subcategory, subcategory element of that vehicle. So you have performance of the vehicle, you have the technology of the vehicle, and say, this is what I'm going for. I'm evaluating this because of this in my region. Then we have another approach, and this approach is called ML2A, which is a multi-level, multi-layer approach. And this approach is a little bit, it's much more elaborated, is an approach that will include several vehicles, which we term here as levels. So you can see here we have several vehicles that we are expecting that they will use the infrastructure. And each vehicle is here a level. And each vehicle will have different characteristics which are attached to the vehicle. So you have a set of vehicles that you want to evaluate the alignment for, and then you try to match the vehicle with those existing in the database. The match up is very important because we have different categorization in different countries. Some countries are following EU categorization. Some other countries, they do have their own categorizations. In general, there are not that many differences, but still the terms are different and the weights or some dimension can be different. So one should be able to match up the vehicles that he wants to assess and those existing in the database. And we have to make sure that you don't really give large ranges. For example, if the weight of the vehicle I am assessing is 10 kg, and in the database I find a vehicle of same category, which is 9.5 or 10.2, it is maybe better to go for 10.2 due to the reduced difference. So you have those kind of choices to make. And indeed, you know that if I'm using this vehicle, which is quite close to what I'm doing, I'm not really using the same vehicle that is actually using my infrastructure. You have to have in mind that you are actually populating your results or enriching your results with uncertainty that you should be able to assess, and we have way to do that. So you have levels here, and then you have layers here because each vehicle can have several technologies, and you may have several different power train and several laws, etc. So you have all those things together, you map them, you decide the set of vehicle, you have the layers, and then you go with the information to the database that we have, which is provided by European Union. It is called IMEP. And then you collect the models. You get the models for each vehicle and each layer. You may end up in one analysis with, let's say, 42 layers here or 100 layers. So you can handle it, and then you get 1,000 models that you have, non-linear models. And then those models are just given for the components that you are looking at. You are looking maybe for fuel consumption, for NOx, or for things like that. What you will get from the database is you will get for each component that you are looking for, given the technology that you are using and the vehicle that you decided to use, you will get at each slope, not really each slope, you have 7 slopes here. You will get information about which model you can use to estimate the fuel consumption. You can use to estimate the emission, which can be NOx or CO2 or CO or PM, etc. You will get those information for a slope, for discrete elements in the segments. The slope are numbered from -6 to +6 with the increment of 2. So you will have a model giving you, for example, for a truck which is 40 kg and which is using the technology of, let's say, Euro 5 with an after treatment process of EGR. And you take, for example, for the slope, 2%, you will have this model, model A for fuel consumption, model B for NOx, model C, model etc. for different emission compounds. Then you have to adjust those models to balance or to correct them with the surface, the type of surface that you have, because the type of surface of the road, each surface type also denotes rolling resistance, and the rolling resistance will have a kind of effect on the calculation or on the performance of the vehicle. So you need to adjust for the rolling resistance. And then once you get the corrected values, here the rolling resistance will be just a discrete number that you can just multiply with the full equation of the model. Then you go for the environmental modeling. And the environmental modeling, you need to have some decision variables for you to be able to use in the optimization model. So you have here the decision variable for this model as it is presented are segment length, road slope, curve length, and radius. Then you run the optimization model. If the optimization is not satisfactory, which can be the case, I had that problem many times when I ran my own model, you have to go back and remodel your process. The only thing that can be wrong is the way you try to model the system. So if you can get results, then you will get adjusted alignments. Why we call them adjusted alignment? It's simple. It's just because you have the choice to tell the industry or the road designer that, okay, I like this alignment that you provided to me, but I think we can control a little bit of NOx because we are expecting more traffic in HDVs of, let's say, 100 kg, and we know that they pollute a lot because they work in lower speed, so there will be a lot of NOx. And if temperatures are favorable, we can end up having a lot of, ozone precursors. So we want to control NOx mainly as a decision maker or as government law. So please, we want to decrease NOx by 5%, and then we get disalignment. Do you think disalignment is feasible? So we don't leave you with that question in mind that the alignment is not feasible. We make sure that in the modeling process, you have all the condition met there. So if there should be a curve, if there should be a given length, if they should respect a radius, the model will try to handle it in a proper way. So what you have to do mostly is to look at something else like maybe cost or maybe the site that the road is passing or things like that that can be made by yourself as a decision maker. I lost my way. Okay. I can't move on for some reason. Oh, sorry for that. Okay, so how can you select a test vehicle? How can you select a set of vehicles? Well, that depends on the country, on the region, that depends on the sector, but we provide you with a table which can help you, what you can use as a guidance if you want to select a type of vehicle. First of all, we say here, for example, the distance traveled by the type or the category of the type for 1 year or for the last 2-3 years should be above 10% of the total travel distance in the country or in the region. I am in the region, I have a road network, and I know that I'm trying I'm designing a road, and I know that roads in that region, they are traveled by this type of vehicles, and then among those vehicles, there is 1 or 2 or 3 that travels a lot. So above 10% is a good indication to pick the vehicle. And you should look at the type of fuel that the vehicle is using and the type of powertrain that the vehicle is embedded with. So you have some criteria that you can use. And when it comes to picking one particular technology, then you have to look at some other factor like average age and regional trends. For example, if I know that the average age of my park is 8 years, I cannot go and say that the vehicle technology is Euro 1, because Euro 1, that's back to 1992, and I have vehicles of aging more or less 8 years. So it should be somewhere between a Euro 4, Euro 5, or Euro 6. Then you make a proper decision. So we have you have policies, you have documents to go through and do those type of decision. And here is a very short, a very small sample of the model, which is an environmental model. Here, I don't think I have to explain you everything, but you can see the functions that we are trying to minimize are here. And you can also see the type of constraints that we are imposing to the system. I have to tell you, for example, that the constraint H3 X here starts from -6 to +6, which is telling you that after running your optimization, when you are trying to adjust your road, you should not go, you shouldn't have a slope, a segment whose slope is above 6% or below -6%. Those type of constraints, for example, because this you can find in the road design book, N100 in Norway. So you have to rely with the legislation in place in the country. And for example, here we are trying to minimize fuel consumption, which is one performance indicator. And in case I'm using a single level approach and I want to minimize to have control of fuel consumption, so my indicator will be based on fuel consumption here. And then here I have the type of fuel, and I am assessing the distance DR, which is direct and reverse. So I'm assessing the road in both senses. And then you see that the function is depending on the speed. So when you design, you have a speed limit, and you can test a bunch of speed from below the speed limit up to the speed limit and see if you have to rearrange your speed limit to remake the decision about the speed limits or not. And when we have an alignment that has been designed by a consultant and they give us that alignment, we don't want to change that much the alignment. We want to rely as much as we can to what they proposed. So here we have a good function that is trying to control this. We say we don't want to induce a lot of changes. Please reduce the changes, but try to achieve our goal, which may be controlling NOx, controlling CO2, limiting it up to a certain level of a certain amount. So we have some selected case here. We tried to work on a small part of E39, quite close to Oslo. And we used for our first analysis 57 kilometers of roads, and we had 407 slope data points that we looked at, and a speed limit of 80 kilometers per hour. So what you can get as the results, I don't know if you are able to see it where you are, is something like this that you have above here. So you will have a different type of elevations. So if you get the alignment, you get the segment distance, and then you get the slope, you can generate the elevation of the road. So you can understand more or less how the terrain, the infrastructure as a terrain itself would be going. So the first one that you are seeing above here is maybe the alignment that you got from the consultant. And then you try to make a decision. You say, if I get the alignment from the consultant, I call that alignment 0% reduction. I didn't do anything in the reduction of that alignment. And then I assess the alignment, I generate my elevation. So it will be going like that. But what if I want to induce very, very, very small difference, very small changes in the slope? So I want to get an alignment with the least slope changes. Then you start running your optimization model, and you are seeing clearly here that the trend is that the alignment, the elevation is decreasing, and as far as you keep going on, you will end up having almost flat terrain. So I don't say really flat because there is an inclination here, because it depends on the starting point and the ending point. If both points are not at the same elevation, the alignment will not be really flat, will not be really zero. You will still have something as a slope. But this may or may not be achievable, because if you have some location, some people up in the mountain there, and then you say, I go for this one, you will not reach them. So if you want really to help them to have access to something, you will not reach them. So you should be able to make a correct decision in that. And here we try to play with the slope limits, The legislation is saying 6%, but we say, what if we go 5.5%? What if we go 5%? What you can see is that in 5%, there is no, you don't go really down, really below the alignment that achieve the least fuel consumption. But in others, you are allowed to go. And I don't know if this is good, because this will be maybe a huge cut. Imagine here to here, here to here also. You will cut again, and then you may induce some more environmental impact. So the decision should be done in the correct way. And then we try to assess our model. If we run it for 0%, 5%, 10, 15, 20, and we run it for total fuel consumption minimum, what does it mean? It means that if you use the road, you use an alignment. Even if you go for a flat terrain, you will always consume something. So minimum fuel consumption will never be zero. Since it will never be zero, there will never be zero emission. So there will still be something that you will consume. And what you want to do is to be able to control a certain type of emissions. You'll be able to help people to do some savings, because if I'm saving 5% every day, after 1 year, it will be a lot. And saving in emissions, saving in money, saving in everything, that will help you to try to create a good balance. And we tested the model, our model that we got. We say the slope distribution of the model, what that we got after running the model, and how much they follow along the road. I mean, if I run the first model, it is obvious that the initial alignment that is not changed has different type of slopes that you can see here, from -10 to +10. This is an alignment that we download from a card from Statens vegvesen, and sometimes it is you have slopes that can go to 14. So you don't understand, because the legislation says the maximum is 6, +6 or -6, but you have -10, -14. And you try to say, okay, let me stick with the legislation, and then you go, you will see something will happen. As long as you keep going down, what you get is that the roads will end up being around the slope of 0 here. But you will still have some slope that will not be 0, some slope data points. Some segments will have a slope different than 0. But the majority of the road, a large amount actually, from 25 to 75, which means 50% of the road, was just changed to get to the slope of 0. That may induce additional cost. And here we give a slope range factor according to the maximum, the limits. You can have the value in percentage. You have this. This is the share of road with less than 10% slope difference. So I try to change the slope that I got from the consultant, and I want to see if my road has changed entirely, or there is still a huge amount or a good part of the road that has not changed dramatically, that I can achieve to do in type of intervention. Because sometimes you may need to do an intervention on an existing road, and you don't have to consider the whole infrastructure. You want to do an intervention somewhere. So you should be able to identify the parts of the road that need intervention. What we did here before, what I showed you before, the way the alignment was unfolding here, was also related to the optimization technique that you use. Here we applied a goal programming approach, and you see that everything looks nice. You go from up to down, and which has a meaning. So if I'm trying to decrease, what I'm doing in my alignment is that you shift the alignment down, and you try to getting flatter. So flattening and shifting down was the main behavior that we got here. But if you change the optimization technique, you can end up with something like this. So the alignment will not always be shifted, will not always be flattened. You can have different weighting factors, and then the optimization technique may allow different type of results. So here is an example of them, meaning that sometimes it is better to stick with one technique or not. but also you should look at the advantages that the one technique is giving you or the other one is giving you to see when you look at cost or you look at environmental impact or some social effect that you have. So here is more or less the same model. We run it with different vehicles, and we got we selected different speed, and we got different type of alignment according to the speed and according to the reduction profile that we are trying to give. So, and then here you have the evolution of fuel consumption. So if I assess my road and I generate my alignments based on fuel consumption, what I get according to the speed is that if my vehicle is fully loaded, I will be consuming more, and that is normal. And this is following a normal trend. If the vehicle is half loaded, you will consume, let's say, in between the fully and the empty. And if it's empty, you will consume lower. So the lowest consumption is with empty. The highest is with fully loaded. But once you go down in speed, what you are consuming is increasing. And it can go even more. So for speed of 105, I was below 55,000 grams for this distance of the road that I took. For speed of 100, I went a little bit close, and then I ended up being above 35 for the speed of 60 kilometers. So imagine a vehicle running on a speed of 40 in the road, which means he will consume a lot. This consumption is due to the differentiation that you have in the stop, and the variability is counting a lot. And here you have CO2 profile. CO2 is following the fuel consumption, but something a little bit, something to look at is also the trade-off between pollutants. CO2 is going down, just like fuel consumption, but NOx is doing the opposite. You end up having more NOx when the vehicle is empty. And when the vehicle is empty and the speed is lower, you will produce even more NOx. So when the vehicle is running empty, NOx is welcome, so to say. Okay, that was the result that we achieved. And here I have other things that we are trying to do. We are developing scenario. We are trying to work on the robustness of the model, and we are trying to develop a much more advanced environmental modeling, which will include also the construction phase, the air fog balance, and everything. The model is there. We are running it. We are improving it, and put it in our tool. The traffic will not be static. The traffic will be changing. It will be dynamic. We may have different type of vehicles. We may have electrical vehicle. We may have some conventional vehicle. Working on evaluating under eco-driving models. So we need to be able to make a decision when we use a multi-level, multi-layer approach to say, okay, if the time horizon of the road is 50 years, how will the traffic evolve, and select the desirable scenario and try to go for that scenario to see which type of alignment we will have and what the geometry will do. In that respect, we did one work that was also, has been published also. And we look at the effects of the eco-driving behavior. If the vehicle is driving eco and it is a HDV, what is the effect of the slope on that? And we applied a different technique here. We introduced a bi-leveling and split apply combining approach. We developed some model that we can use with respect to fuel consumption only because we didn't have any equipment to measure the emissions. So if we try to assess the alignment, we will just base our analysis on fuel consumption. But here, the best model was a second degree model with good statistical proof. And another work we did is to try to understand which factors are influencing the alignment design. Because when we go for environmental modeling during construction phase, we must be able to identify what's in Norway is important, what in Norway is weighting the most. And we did a work that is also already submitted, and we figure out that the huge part is still traffic. So traffic counts for 65 to 55%. Construction is counting about 10%. So We don't know exactly how the 10% will be, but we still understand that traffic is still important. So even if you stick only with traffic using our model, you are quite close to achieve good things. So this is the state of our works. We have some validated work already, and we have some work that are ongoing. So we hope that we get them through. We are working on them. We think time will allow us to go more in detail and have a full stochastic model that will capture the dynamic of traffic, the different levels, the different layers, and be able to give a good guidance for decision making in those who are working with that. And where are we heading? So the team is aiming to go for highways of the futures, which means we are putting on place standards and helping in decision makings, developing tools that can be used, at least environmentally wise, that can help us to go towards the highways of the futures. And what we mean is that what you see in the upper picture here is an integrated, intelligent, and environmentally optimized road planning and design. We mean we use simulation, optimization, but we focus also on the environment, if not only in the environment, when we are planning and designing. And we can achieve all those things that we are seeing here. We can reduce fuel consumption, we can reduce emissions, we can reduce the money that people are spending and the money that we are spending in designing the road, and we can step bit by bit decarbonize the whole economy. So what we need to do is to look at those things here. It should be traffic oriented. We should balance work. We should reduce rights of way costs and make it feasible, reduce the overall cost, increase execution and operationality. If we do this, and I think it is achievable, we can reach the goal that is ours. Thank you very much.
Thank you very much. Applause, it says here in the regards. I had a question for you.
Yes.
Why does NOx go up with an empty car? I didn't understand that.
Well, the first answer to you will be that I use the model that exists, so the model is indicating that. But there is a trade-off generally in the engine behavior. When you're doing combustion, what you try to achieve with your engines at higher temperature is you want to convert carbon from its most reduced phase to its most oxidized phase. That's why you get, for example, CH4, which is methane. You put it in the engine and then you burn it, you get CO2. So you cannot get something else. But when you go up in temperature, the maximum operating points for CO2 reduction is favoring the formation of NOx already in the engines, because when you have air entering the engines, in the air you have oxygen and you have azote, nitrogen. So at a certain level of temperature, if it is going higher, what you want is to go higher because you want to carbonize the fuel and get the most reduced value of your fuel. NOx will come out. So it turns out that NOx is formed when you are in the maximum operating engine for CO2. NOx will be higher, but when the engine is empty, it is the vehicle is empty. It is much easier for the engines to get really higher temperature for some reason, given the slope, and then to get higher generation of NOx. That one will be better to run an experimental analysis of that. But people are claiming that empty, the vehicle is going maybe faster or I don't know what, and the engine is reaching higher temperature for some reasons, and that is helping the formation of NOx. I do agree with them to some extent, but the model is telling me what you're seeing, so I stick with the model, but it will be better to run an experiment and to see what we can find in that.
I also have a question.
Yeah.
Yeah, Tom Norbeck. If you can go a few slides back.
Okay. Just tell me to stop.
One more. Well, a few more, but I'll tell you. Okay, back.
Here.
Further back, please. And further back. Back.
Yeah.
And back.
Okay.
And back.
Okay. Yeah.
And one more, I believe.
Okay.
And one more.
Here.
Yeah. It's, yeah. Now, this was one too far.
Okay.
One more.
Yeah.
Yeah, okay. I'm seeing that footnote number 2. Electric hybrid vehicles will be considered in regions with conventionally produced electricity.
Perfect.
Why not all kinds of electricity?
Well, if you are, let's say, generally operating in a country where hydroelectricity is the main source of electricity, then you can claim that you are going cleaner. I mean, you are going greener because you have electricity produced by hydro. But if you are in a country where electricity is from coal or from any type of fuel that is polluting itself, so then electric vehicles, in terms of pollution, they need to be incorporated in the traffic mix, so that you can put them in. We have a way to put them in the model and to quantify. Actually, I call it to allocate the emissions from the grid, which electricity is from coal or from fossil fuel. Those emissions are integrated in the model and then counted as the other emissions from other vehicles using fuels on the road.
Yeah. Well, I have two comments on that. Yes. One point is that it just in the last weeks it came a report.
Yeah.
That showed that it was a CO2 gain even in the most coal intensive electricity mixes in Europe, for instance Poland. I can send you that one.
Okay.
So I'm not sure if that applies only for lighter vehicles or even the heavier ones. I'm not sure, but yeah, it seems what you've been saying is I've heard that before, but there is some new information. And the other thing is that you know you could discuss the system boundary. Is it the vehicle or is it the entire electricity system? Because you know, if we are to meet the climate targets, you have to have both processes as once. You know, both decarbonizing the electricity and decarbonizing the vehicles, so to speak. So we don't have time to wait for both. You know, we need to electrify both, and this could be an argument for putting the system boundary around the vehicle, and then you would have an extra argument for decarbonization. You know, because if the vehicles are introduced, you have introduced the potential. Yeah. And then that could be an extra push for decarbonization of electricity production.
Yeah, I totally agree with you, and thank you for pointing it out. And I would like to read the report. But there is something I would like to go against with, gain of CO2. Then I really don't understand what people mean by that. So maybe if I read it, then I can understand. Because if you use CO2, you use a grid that is conventionally run, maybe let's say it has fossil or carbon or coal, then you produce CO2. CO2 is produced, even if it is 2 grams or it is 5 grams, it goes to the atmosphere and it is among the GHG gas. Even if CO2 produced from forest, from biomass, it all goes to the atmosphere and they produce the same effect. Other things that we can wait and reforestation and things like that, which will take place in the long run, but by the time CO2 is released, it goes to the atmosphere and it does something. So I understand that we have to move the system boundary, and I totally agree with you. But the idea was to try to treat electric vehicles and conventionally maybe fossil vehicles in the same base and one-to-one base. Not saying that okay, electrics are always better. We know they are better, but we try to see okay, if they are running from hydro or from renewable sources, it's okay. But if they are running from maybe carbon-based sources, then we may account this for them and try to see if they may balance, they may change something in our alignment. Otherwise, we will have no effect when we use electric cars. So no alignments will be changed because you have nothing to reduce there.
Okay, Gaylord, I have to interrupt here because we are on overtime. Okay. But we have one more question.
Yeah.
Can you see it on the left of your screen? Or should I read it to you?
Yeah, you can read it for me.
The question is from Alf Helge Greaker.
Yeah.
I worked as a bus driver for many years in Bergen City region with many slopes and hills. Yeah. We experienced less diesel consumption, hence less climate gas, I guess, with a 12,000 cubic centimeters, 12-liter Euro V engine, then a 9,000 cubic centimeters or other factors equal. The 12-liter ran at lower RPM than the 9-liter, same hill.
Yeah. And the question is?
All other factors equals. The question was, is the engine size cubic centimeter considered in any models?
Yeah. We are considering. That's what I told you in the multi-level, multi-layered approach. The layers can go from weight of the vehicle, size of the vehicle, cubic centimeters of the engine. So we talk about powertrain technologies, after treatment technologies, and so on. So everything is considered in the model. The model is quite non-linear, and what I'm trying to do is to try to linearize it, and it's a lot of work. So everything is considered, yes.
Okay, then I see we have no more questions, and we are running out of time here.
Yeah.
So we have a thank you from Alf Helge.
Thank you very much.
Also applause. It's a little bit difficult to have the applause coming when all of us are quiet.
Thank you very much.
But okay, then I would just like to remind the audience, we have great presentations and thanks. The next presentation that will come out in this series is the 1st of December at 10 o'clock. It will be Josef Jonsson talking about safe and ice-free bridges using renewable thermal energy sources. So that is the next one. And this presentation will be put online today, and also the movie will be put online. So then you have the opportunity to see it again. Okay. Thank you very much.
Thank you very much. Bye-bye.
Bye-bye.